Good afternoon, ladies and gentlemen. Welcome here at the Technical Forum at the group exhibit Hydrogen, Fuel Cells and Batteries, this year at the Hanover Fairground in the year of 2015. Every 15 minutes, I will present you interesting topics regarding the hydrogen and fuel cell industry. Today's overall topic is the hydrogen production and the energy storage. And for that, our next topic will be high-efficiency MW PEM electrolyzers by China. So please welcome with me on stage Vice President Manufacturing and Engineering, Mr. Timothy Norman. Big hands, please.
Thank you, Monali. Thank you. Thanks, everybody, for coming today. Okay. So today I'm going to talk about Giner a little bit. I'll introduce you to Giner. We've been around for a long time, but a lot of people do not know us. And then talk about our electrolyzer systems that are and new technology advancements in efficiency with new membranes coming to market. We're making some exciting improvements in efficiencies, and that plays into cost reductions of electrolyzers, and then talk about very large-scale PEM stacks we're building today. Giner was founded in 1973, but several of the scientists that started the company or were with the company were actually at the very invention of proton exchange membranes at General Electric and DuPont. We've been specializing in research and development technologies ever since '73, and we not only do electrolyzers, but regenerative fuel cells and electrochemical capacitors. And very recently, we have been doing some very interesting work with oxygen management, gas concentration. But that's not today's topic. Today's topic is electrolyzers. That is where we see our commercial business and manufacturing business. We are 55 people. We are in Massachusetts, near the Boston, city of Boston. Okay, so on the R&D side, we are doing some exciting work in electrolysis with regenerative fuel cell systems for aerospace applications. And I did want to spend just one slide on that. Our first stacks are on board U.S. Navy submarines for oxygen generation for the submariners to breathe. That program has allowed us to develop differential pressure electrolyzers. So we pump in water at low pressure, but generate hydrogen at significant differential pressure above the oxygen. Our aerospace stacks are quite interesting. We've taken our core technology and lightened them up by a factor of 4 so that they can fly instead of sink in a submarine. They're running at very high efficiencies. And because of the issues with microgravity and low gravity environments, we have started running vapor feed electrolysis, which does not require any liquid hydrogen, liquid water and hydrogen separation or oxygen separation. We've also done in the past 1 square meter electrolysis designs. So now on to efficiency advancements, and in particular the new membranes that we've been working on that are coming to market. We've named this membrane the dimensionally stable membrane. We initiated the work because, as many of you who've worked with Nafion know, it's as it changes in humidity levels, it changes in its XY dimensions quite significantly, which is a real problem for manufacturing. And so we included a engineered plastic inside the Nafion material. And that strengthens it up in the X and Y planes and allows all the dimensional change that has to occur to be in the Z or axial direction of the electrolyzer. So when we test it, it has much superior mechanical properties, up to twice as strong as native Nafion, and much stronger resistance to tearing, and far superior to the PTFE supports that are currently on the market. I'm bringing this particular material up now because it's an enabling technology for our very high pressure applications. And at this point, we're in the stage of roll-to-roll process development. So membrane efficiencies are quite staggering. We're already quite efficient with our Nafion 110 membrane, as we've used as the baseline here. So operating at, say, 1,000 milliamps per square centimeter, we're at just over 2.2 volts. The dimensionally stable membrane allows us to get to, at 110 we're at 1.7 volts. And at dimensionally stable membranes, we've achieved even 1.6 volts at such a high current density, which gives us efficiencies on the order of 85 to 95% on a high heating value basis. Those MEAs are using low catalyst loadings as well. Okay, so one of the issues with membranes is obviously their durability, and one of the open questions about dimensionally stable membrane is its lifetime. We've tested the DSMs now for beyond 5,000 hours on the scaled up dimensionally stable membrane at the aggressive conditions of 80 degrees Celsius and up to 5,000 milliamps per square centimeter. This test I'm showing here is at 1,500 milliamps per square centimeter and then 1,750 right here. The fluoride release rates indicate a lifetime of approximately 55,000 hours. Okay, one of the key points of the DSM is it's going to allow us to run at much higher current densities. So we were interested in the effect of higher current density on durability. And you can see here that it took quite a significant knock to increase the current density to 5,000 milliamps per square centimeter. I should say today, currently, our commercial stacks are running at 3,000 milliamps per square centimeter. So after some research and development, we found a chemical that we could imbibe into the dimensionally stable membrane that allows the advanced DSM to recover most of the life, again running at 5,000 milliamps per square centimeter. This portends a much reduced cost or higher efficiency on the electrolyzer stacks in the near future. Okay. The cost of hydrogen production is really a trade between the efficiency of the stack and the capital costs of the equipment, obviously. The biggest cost, of course, is the feedstock. So running at a higher efficiency reduces the impact of the feedstock price. Running at higher current densities allows you to run with fewer cells, a lower cost stack. Okay, so this is more about stack cost reductions here. We started a program with the DOE at the mid-2000s to decrease the cost of the stack. We did that by reducing the parts count. And Navy stacks have over 40 parts in each individual cell. That's over 2,000 parts in a stack. We've now reduced that by a factor of 4. And as you can see, the part count reduction is a commensurate decrease in material costs. The interesting thing is that as we go forward here, we're portraying, after a 60% decrease in costs over this past few years, another 60% decrease in our costs. Okay. I'd also like to say that our commercial electrolyzer was the first to market at 1,700 milliamps per square centimeter, 47 kilowatt hours per kilo. We're seeing rapid adoption of that technology. We're currently selling into 7 different countries, and the unit is CE compliant, so it's ready for Europe. On the R&D side of things, we're doing some very high pressures. So we have run the electrolyzer cells at 5,000 psi, which is 350 bar differential pressure generated directly in the proton exchange membrane. So we're eliminating at least one, maybe two stages of mechanical compression in such a system, reducing the complexity, and much lower maintenance because of no moving parts and contaminants. One such implementation of a high-pressure system was this project where we did a home refueling unit. Of course, the balance plant costs are quite high for running at 5,000 psi, but we were able to put together a quite nice compact system that would fill a car with half a kilo of hydrogen overnight. Our technology has been validated at the National Renewable Energy Lab in Golden, Colorado. Back in 2012, we took our system and ran it roughly 27 bar and 2,000 milliamps per square centimeter, 1,500 to 2,000, with very high stack voltage efficiencies, over 87% high heating value efficiencies, and exceeding the DOE 2012 target. We've also validated the stack at Arriva's Green Energy Box in Corsica, France. And you can see that here where the unit was generating hydrogen off of solar power. Okay, so finally I'll talk about larger scale PEM stacks. It's being led by market demand. We started about 10 years ago producing lab-scale hydrogen generators at just 50 liters per hour. We're now commercially selling up to 90 normal cubic meters per hour stacks. And we're currently developing a 220 normal cubic meter per hour on a megawatt scale electrolyzer stack that you can see at our booth, C40, directly behind us here. So our target markets there are intermittent renewable energy sources, backup power, mobility, and power to gas. And here's a slide with a mock-up drawing of the large stack, and you can see it's in the system here as a smaller part. So the megawatt stack leverages all the design work on the earlier stacks with reliability, efficiency, and cost just in line. So I think I'm wrapping up here, just on time, Monolith. So just to summarize, our capabilities continue to grow to meet the market. We're increasing efficiencies, we're increasing our pressures, and we're increasing the hydrogen output dramatically. So efficiency is the key to competitiveness. Obviously efficiency is important, but you can trade it for lower capital costs, which for certain applications is more important. Okay, thank you very much.
Thank you very much. Big hands, please. Unfortunately, there is no time for questions. You can take all your questions to booth number C40.
Yes,
right?
Thank you very much.
Thank you very much. Next talk will be about the first commercial power-to-gas plant with biological methanation that is going live. So only in 1 minute time we'll have the next presentation by Microbe Energy.